welcome back. We're now going to dive head first into calculations because that's important. Here we go. So, wrong way. Earth has a mass of 6 times 10 to the 24 kilograms. Not a value you need to know, it will be given to you. Average radius of 6,4 times 10 to the 6 meters. Then they tell you a communication satellite, so it sits atop the Earth, has a mass of 850 kilograms, moves in a fixed circular orbit around the Earth. So we have the Earth, and then we have the satellite that then moves around the Earth, okay? And it stays the same distance above the Earth. Then they say calculate how many kilometers above the Earth's surface the satellite moves if the Earth exerts a force of magnitude 7,500 newtons on it in order to keep it in the specified orbit. Now, there's a couple of things we have to look at here. They want the kilometers above the Earth's surface. So we recognize they're asking for a distance. Generally, the first part of this question we can do. They want a distance. We can do that. We have enough information. That's where we're going to start. So F is G, M1. When it's a planet, we usually use a big M. That's just because planets are big. Over R squared. We know that the force that it experiences is 7,500 newtons. We know G is 6,67 times 10 to the minus 11. Let me just write that so that that looks like a times. Okay, it's all about being neat. We know that the satellite is 850. We know that the Earth is 6 times 10 to the 24, and we need R squared. I'm going to take the R to the one side, so we've got R squared, and 6,67 times 10 to the minus 11, 850 times 6 times 10 to the 24, and that's all going to be divided by 7,500. I cannot do this in my head, so we get our calculator out. Let's just make it so we can see what we're trying to do. Okay. So 6.67 to the minus 11 times 850 times 6 to the positive 24 gives us the top part. Now I'm going to take that and divide by 7,500, and that gives me 4,5356 times 10 to the 13. But remember, that's R squared. So straight away, because I want to keep that answer in my calculator, I'm now going to square root it, because that gives me R. Square root my answer, and I get, we get a nice big number. So here we go, and this gives me, I'm going to have to put the calculator back up because I can't remember that number. 67, you know what? I'm going to put it in scientific notation. Let's just make our life easier, and that really is fine. So 7, and we need 3. So it's 6,73 times 10 to the 6. You absolutely can keep it with that whole number in if you want. I'm changing it to scientific notation because they tell me that the radius of the Earth in scientific notation. It just makes it easier. But we're not finished for 2 reasons. One, they want my answer in kilometers. 2, they want the distance above the surface. If we go back here, oh wait, there it's gone. So, what I'm going to do is I'm going to quickly just take out the calculation. I'm going to keep my R. I need to show you what they're asking us for. So we're going to take this away, because a diagram always helps. There we go. Some of those don't want to go. Anyway, so this is, the Earth is here, and the satellite's here. The radius of the Earth is to here. That's the radius of the Earth. They want to know what this distance is. The R that we've calculated is this entire distance, which is a little r naught, which is that. So, the height above the Earth is going to be that value, because that's the distance from the center of the Earth, minus the radius of the Earth. And that's not minus 6, that's got to be plus 6. That's ridiculous. Then it would be somewhere in the center of the Earth. There we go. That would just make a very silly question. So, calculators. We like calculator. So here we go. So I'm going to take my answer, 6.73 to the 6 minus 6.4 to the 6. And we get 3,30 times 10 to the 5. But that's meters. Oh no, one more step. Has to be in kilometers. So now we've got to remember that there are 1,000 meters in a kilometer. I need to take that answer and divide by 1,000. Take my answer, divide by 1,000, and I get 3,30 times 10 to the 2. Now it's in kilometers. And some of you probably could have told me that there was 330 kilometers. You can leave it in scientific notation. So here, and they like to ask these questions with the Earth, be careful. The key was above the Earth's surface, not from the center. So it's got that extra little piece to it. Okay? That was fine. We got that. That was a nice substitution type question. But what if we do a ratio question? So, we have a large planet which has a mass 400 times and a radius 25 times bigger than that of the Earth. This is a big planet. It's much bigger than the Earth from a mass point of view. But it's also got quite a long, bigger radius. So it may have a bigger force of attraction. It may not. We're going to have to work it out. If a man weighs 500 newtons on Earth, what will his weight be when standing on the planet? Weight is force, not mass. I don't even need to work out the mass of the man. Watch. Right, so we know the mass of my planet is 400 times the mass of Earth. The radius of my planet is 25 times the radius of the Earth. We also know that on Earth, the man experiences a force of 500 newtons. They want to know what force will he experience on the planet, the new planet. With ratio problems, the easiest way to do them is to find something you know. So let's start with how I would calculate his force on the Earth. It would be G, mass of the man, mass of the Earth, radius of the Earth, squared. If the force of attraction with the Earth and the man's weight are the same thing, so this is equal to 500. I've got a value. Stick with me. If I now look, if I now look at on the planet, so the force of the man on the planet is G, mass of the man, mass of the planet, over the radius of the planet squared. I know how big the mass of the planet is compared to the Earth, and I know its radius. So I'm going to put that in. I'm going to go G, mass of the man, times 400 times the mass of the Earth, over 25 times, it's got to be squared, the radius of the Earth squared. We're now going to rearrange it so that I have all the constants together. In other words, 400 times G times M times ME, 25 squared. I can't do 25 squared in my head. So let's just quickly do that. 25 squared. Okay, let's take it out of the scientific notation to make it a bit easier. 625. So that's 625 times RE squared. Now watch the trick. This is when it gets fun. So if I go over here, this little part here, that is the same. This, what I've circled in blue, is the same as that. It's exactly all the same formulas, same symbols. So that means that little part that I've circled in blue is equal to 500. How does this help us? Well, it means that I can now go, let's do it over here. My F is now going to be 400 divided by 625, because that's the first part, times by 500. Oh, look at that. So now we take our calculator. All right. And we're going to do 400 divided by 625 times by 500, and we get 320. So even though this planet was so big, its mass was so much bigger than Earth's, because its radius is so much bigger, actually we have a smaller force of attraction. It's only 320. That's nice. Did I need to know the mass of the Earth? No. Did I need to know the radius of the Earth? No. It's a ratio problem, okay? And on that note, we're going to take a short break, and we'll be right back.